Welcome to the third lecture of Mitchell-Luskin. It's on relaxation and pattern formation in incommensurate 2D materials by configuration space.
Okay, thank you. Thank you for everybody who's still alive after 4 other tutorial lectures. So it's a lot to absorb. Okay, so what I'm going to kind of switch to mechanics here. And so there is interesting mechanics in these incommensurate 2D layers. I'll explain, what's interesting about it in a minute. So the first half of the lecture, I would say, is kind of a, let's say, informal, naive approach to the subject. And it gets the answer for bilayers, but it doesn't give us a model for multi-layers, say 3 and above. So that's going to take a little more sophisticated kinematics, you might say. So first we'll start informally, and then we'll kind of redo it in a more kind of formal, systematic way. All right. Okay. So let me just start off with a few slides that you've already seen before, and I don't think anybody's new here. But okay. So here we have our 5-layer system, and so for the first part of the lecture, it's going to be for bilayers. So it could be graphene on molybdenum disulfide, or it could be graphene on graphene, etc. Here's the top view of the atomistic structure again. Let me just say one thing that's you might say, okay, if I want to know the mechanical energy of a bilayer system, and so let me just so if it's periodic, right, then the Cauchy-Born strain energy does the job, right? But if you don't have periodicity, you might ask yourself, how might you define a strain energy density? So you might just say, okay, I'm just going to go and take a large body limit of 2 incommensurate layers, to even 2 incommensurate chains, and ask how does the energy per unit length or unit area, how does that converge as the size of the body goes to infinity? Now that actually, it turns out the convergence can be very, very slow. Okay, and all these kind of questions, they all come down to sort of Diophantine approximation, really approximating irrational numbers by rational numbers. I mean, this is the whole subject of number theory. Of course, some irrational numbers you can approximate better than others. So we see all of that in trying to define let's say, a strain energy density as a large body limit. Okay, so we've seen this figure before. This is just sort of a nice explanation of what angles have supercells and how large the supercells are. So let's say, so the blue atoms are, say, you can think of as the bottom layer of say, graphene, and then you ask, as you have a top layer of graphene and you twist on it, what angles give you a periodic structure? And of course the period is going to be larger than the period of each single layer. And so this here shows you, for this angle theta 1, right, we have a unit cell, a period of 7a, A1, where A1 is the lattice spacing of the single layer. Okay, and we see also that for small angle, any possible periodicity will have a very large kind of super lattice. Okay, so this is a nice diagram I like. Okay, so this starts the subject here of mechanics. So okay, so what do I? So I think that why don't you focus first here at this picture B. Okay, so if I have suppose I have just say 1 layer of graphene on another, and the configuration of one on another, right? It can be, and let's even think of saying there's even no twist even. Then let's say if you put the one layer exactly on top of the other, okay, that's called AA stacking, because remember there's A there's A atoms and B atoms in the lattice, right? Okay, so you might think the A atoms are the lattice points, and the B atoms are sort of have a separate little vector forming a multilattice. But when one layer is sitting right on top of another, okay, that should be the highest energy state, the highest energy stacking, because the atoms don't want to sit right on top of each other, right? Because then they have electrostatic repulsion, right? What the atoms like to do is it likes to be, say, in what's called an AB or AB arrangement. Now, say in the AB arrangement here, you see that corresponds to some kind of shift of the, let's say the red to the right or the blue to the left. Then in that case, these atoms here are sitting right in the center. Let's say I guess this is the B atom of the top layer, you might say, is sitting right in the center of the hexagon. So that's real good. So it's as far as it can be from any of the blue atoms. So in this configuration, 3 of the 6 atoms in the hexagon are sitting right in the center of a hexagon. So that's the best, energetically, that's the best possible arrangement of one layer on another. And so I'm just kind of drawing an energy landscape of the say dysregistry or shift of one layer with respect to another. Okay, and then we keep sliding. Then we hit a saddle point. Then we get to this other case where we have B sitting on A. That was A sitting on B. And then finally we get back to AA. So this is kind of like a one-dimensional view of this energy landscape. A represents the full, two-dimensional view of the energy landscape of one hexagonal lattice on another. So we see, right, this is the high energy. So that's when say the red layer is sitting right on top of the blue layer, right? And then these here represent the AB and BA kind of states. So this is our energy landscape. Okay. Now, so this is comes out to be one of the simplest bistable systems you can think of when you have two states, right? And you're trying to minimize, right? You normally lead to some kind of patterns. Okay. So we'll see how that goes. Okay, and this shows you experimentally the patterns that are formed. This is a dark field image. Okay, so this is regions of BA, AB, and then we have these interfacial regions. Okay, so so back here, I think we've seen this before, or figures like this. This is simply taking one hexagon and then rotating it at, I don't know how many degrees, I'm not sure. Anyway, so that's one hexagonal lattice rotated on another. Okay, so if you look, and actually, when you see these patterns, what you're seeing are really patterns in the dysregistry, in that vector B. That's what you're seeing here. So you're seeing that the dysregistry is actually slowly varying as we come across the material. And the length scale at which the dysregistry or the pattern changes is a much longer length scale than the atomistic length scale. And in fact, the length scale of this grows inversely proportional to the rotation angle. So the smaller the angle, the larger the Moire cell. So we'll actually compute a formula that will tell us exactly what the Moire lattice, what the Moire cell is as we go along in the lecture. Okay, so now what I want to do is, so I'm going to develop a model for the relaxation. The model is simply going to use actually linear elasticity for the intralayer interactions. So each layer itself, I'm going to have a very simple linear elastic model. You can have more sophisticated things, but it's going to be very simple. But the intralayer interaction, right? That's where this dysregistry comes, right? So that means that the layers are going to want to shift to try to find that low energy state. So what we see here And so this is, with our model, this is what we compute as the minimizing state. So we still have the, the same Moiré length scale, but what we've done is we've kind of, so this is like our BA or AB region, and that's the low energy state. So we've actually increased the low energy state, right, at the expense of creating these sort of domain walls, right? And these are the AA states, okay? So this is a relaxed pattern. This is the real, I mean, this really is what a real material would actually form, okay? So now, okay, so what we're, of course, you know, why is it important to know about the relaxed pattern? Because, in fact, you know, I talked this morning about the density of states and conductivity, all these electronic properties. You know, we have to actually modify that, it's not too hard, to actually include the relaxed positions, the interactions. So if you really want to have a realistic model, you have to include the mechanical relaxation of the bilayer or trilayer system itself. Okay. Now one of the things, one of the things about our methods is pretty much, well, as far as I know, everything else in the literature does these computations by choosing one of those special angles where you have periodicity. Okay, and they go right to a periodic problem, and then in that case, these cells, right here you have a, right here you have your kind of your Moiré lattice vectors, okay, and then you have a unit cell, and when you choose one of those special angles, right, all the other cells, the atoms are strictly periodic with respect to that Moiré cell. It's a periodic pattern, okay? Now this is computed at an angle that doesn't have a periodic, there's no periodic structure. So in fact, even though it looks what it looks like here, this looks sort of periodic, right? It looks like if you look at this cell, like that could be an AA and that's an AA, and they look pretty close, but in fact they're not. They're actually some kind of aperiodic modulation going on. So it's not really periodic, okay? So it'll be, when we derive a continuum model, the continuum model will be periodic, but that's because if we take this picture, even though it's aperiodic, and we scale things down, we end up with a periodic model, okay? Now that's true only for bilayer systems, okay? So again, the ultimate model I'm going to derive, okay, can treat, say tri-layer, four-layer systems, and there we don't have any two-dimensional repeating pattern, any real kind of Moiré cell, except at very special angles, and now the computational problem is going to be higher dimension. So we'll come to that. Okay, so here's here's two pictures from images from Philip Kim's lab, and so this is twisted. This is the twisted bilayer graphene. So what this is okay, how do we get these? Okay, so what you do is first you get a diffraction pattern. Okay, so you diffract off your twisted bilayer graphene or your twisted bilayer molybdenum disulfide, and diffraction is simply taking the Fourier transform, right, of the positions. Okay, now but because it's not really, okay, so there's obviously a huge theory for periodic problems, diffraction, taking a Fourier transform of periodic structure, but in fact, we have the fact that we have aperiodicity means it's a little more complicated, well, actually a lot more complicated, and then we go from this diffraction to these pictures, right? So we're not really, like, so this is like the raw data. The raw data is the Fourier transform, and then to get back to real space, right, we have to then take an inverse Fourier transform with some kind of like window, okay? So basically, what we have experimentally is diffraction patterns right, Fourier transform, and then inverse Fourier transforms, giving us that was called a dark field image. And it's still like one of the problems we're working on is an inverse problem of trying to extract this information and ask how sensitive is the actual atomistic positions to these pictures we see. Okay, because this is all anything an experimentalist sees. Okay, so here again, now here just kind of shows you a little bit about diffraction. So again, here's our relaxed, and this is all computation. This is our relaxed structure, and then okay. So what we see here, so B, C, and D represent kind of a zoom in on different parts of the kind of Fourier transform. They're called Bragg peaks, and this just shows you the difference. If I had no relaxation, I'd have two sharp peaks like this, and then as I turn on the interaction between the bilayers, right? Then we have this kind of relaxation forming, right? Instead of that, so we have the relaxation forming, and so we really see a difference in the diffraction, right? In the Fourier transform of the two images. So okay, so this just anyway. So there's some interesting kind of problems here in diffraction and dark field imaging. Okay, so now let's go back and let's kind of develop our model. So, okay, so this is, we've seen this before, right? We describe the Bravais lattice of each individual layer, right? We take the union, right? This is, when it's incommensurate, this is no longer periodic. Here's our kind of precise definition of incommensurability, and then we have unit cells for layer 1 and layer 2. I kind of did these slides where my unit cell is minus a half squared instead of 0, 1 squared. I mean, I'm describing a torus, right? A periodic torus, so it doesn't matter whether it's minus a half, or 0, 1, because it's a periodic structure I'm looking at. Okay, now let's just kind of it'd be useful just to kind of say, okay, what is this vector A1, right? For for an hexagonal crystal, then the lattice vectors can be taken to be 1, 0, and cosine pi over 3, sine pi over 3. So we can define the lattice in terms of the lattice vector alpha. So that's an A1 for lattice 1, right? And then if we rotate to get the lattice of layer 2, we just apply a rotation matrix R theta to that. So that's A1 and A2 for an hexagonal structure. Okay, and then here's our ergodicity theorem again. So in this lecture, H of L is going to be the so typically in atomistic models, say if you've probably heard of things like Leonard-Jones empirical models, Leonard-Jones model, embedded atom method, all these things, when they want to calculate the elastic energy of an atomistic structure, it's a sum over the energy of each atom. Okay, that's called a site energy, and the energy of that atom depends on the displacement of all the atoms around it. Okay, so that's so H is going to be one of those site energies. So this is going to be how we move from our atomistic model to our continuum models. Okay, and then again here just more about the kind of a review again of as we move through the bilayer structure, the disregistry. So I move through the structure, I look at the disregistry of layer 1 with respect to layer 2, then that disregistry essentially fills out the unit cell of lattice 2. Okay, so that's we've seen that before. Okay, so let's try to derive a model. Now, Okay, so there's one little bit of there's kind of an insight here. Well, okay, so you might say, okay, so if I have an incommensurate body and I want to compute its energy per unit area, let's just say I have displacements U1 and U2, and they're okay. And I'm trying to do a continuum model, so they're just functions of R2 to R2. Now we can add this. So I'm just looking at in-plane displacement. You can also do out of plane. Add that in here too, but I'm not going to do that. Okay, so here. Okay, so here's our large body limit. Okay, so we take the intralayer energy. That's just the energy of layer 1 if there was no layer 2. Okay, and then it's just a crystal, a two-dimensional crystal, and we could use whatever you want, Cauchy-Born, linear elasticity, et cetera, et cetera. Here's the energy of layer 2. And then now, how do we account for the energy of interaction between layer 1 and layer 2? Okay, so this is key. If there was no interaction between layer 1 and layer 2, right, the ground state would simply be two lattices. Okay, there'd be no reason they would shift from their, because the lattice is the minimum energy structure of each layer, say graphene, right? There's no reason we would actually have any displacement at all. But now remember, from those pictures, atoms of say layer 1, they like to sit, they would like to be in the center of the hexagon for lattice 2, okay, and vice versa. So we can account for that by what's called a generalized stacking fault energy, which I'll describe a little more in a minute. Okay. So what is a generalized stacking fault energy? So if you take, look, you could even take two crystals of any sort, okay, two bulk crystals of any sort, and let's say they have they have a plane. They're like half spaces or whatnot. You put them together, and now then and you shift one layer with respect to another, okay, then the energy, right, the energy changes depending on how the lattice of, say, bulk material 1 is oriented with respect to bulk material 2. I mean, if they were the same crystal and you just cut a plane through it and then you just tried to shift, then the lowest energy state would be put back together in the original lattice. But if you start shifting, then in fact there's an energy cost to shifting the layer with respect to the other side. Okay, and this is all over the place in mechanics. This generalized stacking fault energy, as you can imagine. Okay, so now it turns out that the generalized, so B21, or with that B, this just means the energy of layer 2 with respect to layer 1. Okay, I mean there's also an interfacial energy of layer 1 with respect to layer 2, right? And that's just depending on the relative orientation of one layer with respect to another, which is given by the dysregistry. Okay, so now so we could write that as, so that's given by this function here, f. Now the generalized stacking fault energy is actually something that can be computed to very high accuracy by density functional theory quantum mechanics. Okay, it just takes you just have a small unit cell computation, and you exploit symmetry, and you can describe the generalized stacking fault energy with, say, 6 parameters. If you look at our paper, 6 parameters, nails the generalized stacking fault energy. Okay, so the generalized stacking fault energy, right, is a function of the unit cell of one layer with respect to the other. Okay, and this is what it looks like for graphene. This is this molybdenum disulfide. Remember, the molybdenum disulfide, a more complicated hexagonal structure. Okay, So the molybdenum is the brown atoms, right? And the sulfur is the yellow. Okay, so now if we just stack one on another, then whoops, what am I doing here? So you stack one on another. That's called 0-degree molybdenum disulfide. And then it also has some symmetry. They're two kind of energy minimizing states. Here, like BA and AB. Okay, so you have the same thing in 0-degree molybdenum bisulfide. If you take one layer and you rotate it by 180 degrees, it's very interesting. You get something that's not symmetric. Okay, so you get this kind of energy landscape. Okay, and that'll has an impact on the actual relaxation patterns we see. Okay, so here comes the big assumption on this model. Okay, so the big assumption is this: is that So let's say I bring two layers together, okay, and then I let them relax. Okay, let's bring them together. Don't let them relax. Then let them relax. Maybe the atoms just go all over the place. I don't know. But okay, the assumption we make is that the system wants to relax. Remember, we don't want to have all this AA. We don't want to be sitting on top of other atoms. Okay, so so each atom, the atom at lattice point R1, okay, it's gonna want to have a displacement U1, and that displacement is simply a function of the dysregistry of R1 with respect to the lattice R2, the other layer. Okay. So this is you might say the kinematic assumption. Okay. Now, So now it turns out, you might say, okay, I want to prove this. I want to prove this. Now, that's a great problem for somebody to do. Now, we've actually been able to do that in one dimension, okay? Because now in one dimension, it's already rather sophisticated, right? Because in one dimension, what you're really looking at, now you're looking at a chain, and you're looking at so it's like a discrete mapping as you move through the chain, and you're mapping into a circle, okay? And then it's like a discrete dynamical system, okay? So now you can invoke all the kind of fancy dynamical system theory, and we were able to map it into what's called the Aubry-Mather theory, which is kind of an extension of KM theory. So so we carried this out rigorously, and basically what you show is you have something called a Hole function, and this is a very sophisticated subject. We just applied the theory, mapped our problem into this theory. Now the question is, is there a 2D theory? Is there even a 2D Frankel-Kantorova theory? Or not theory, analysis really. So anyway, so we can actually justify this assumption in 1D. Okay, so the 1D problem is like two chains, right? It's just you take two linear chains, you give them some spring constant, then you give them some interaction energy, and of course if the energy between layers, their interaction energy of one atom with respect to the other layer, right? First of all, if that's zero, then again you just have a simple right. Then you just have two periodic chains. They don't deform to lower their energy, and then your mapping now, right, is simply going on you're going around on that circle, and you'll essentially have you'll have some periodic pattern going on there. And now if you just turn on the interaction, that's like a small perturbation to that, and then you maintain this kind of periodic structure, right? Which is essentially what this is. You maintain this kind of Hole function, and then you turn it on higher, then it actually all breaks up, and you get all this kind of chaos. So, but anyway, So there is yeah, so this already is, so this is an assumption that can be verified in 1D. It's a reasonable assumption, and so we go with that. Okay, now, so what is this registry? So this registry is, right, it's the disregistry of an atom, right, is given by this formula, right? We've used that several times, okay, and even in the previous lecture. But what we want is we want to smoothly interpolate this function, right? We want to smoothly interpolate that function, because the disregistry, right, when we have, let's say, a small angle, or the lattice constants are varying not too greatly, then as we move from atom to atom, the disregistry is slowly varying, very slowly varying, okay? So, so the disregistry of one atom to another is slowly varying, and then if we go and just interpolate it, say, take your favorite bilinear interpolant or something like that, then we can characterize we can extend the disregistry to all of space. That's this formula. I'll say more about that later, but this is just interpolation. Because the disregistry is we just move through space if you didn't do interpolation, you'd have a disregistry that was oscillating on the scale of on the atomistic scale, right? But now when you do smooth interpolation, we get rid of that oscillation. Anyway, so this is our continuum. This is our continuum disregistry. Okay, now remember, when A2 was equal to A1, when A2 was R theta times A1, then this is just 1 minus the rotation matrix of angle theta. So the size of this operator is theta, right? So what that says is as you move in space, right? What does that say? It says when you move in space, then the speed of change in configuration space is 1 over theta. I'm sorry, the speed is going to be theta in configuration space. You move at unit speed in real space, the change in the configuration is going to be in the order. You move size 1 in real space, then the change configuration is going to be order theta, right? And that's telling you too the Morey scale is going to be 1 over theta. Okay, so so we have a similar formulation for for the displacements of layer 2. All right, now so now let me let's start in the bottom half of this. Okay, so this is this is my mapping, right? X to when I map from B1 to B2, it's X to 1 minus A2, A1 inverse X. Okay, and then the disregistry of layer 2 to layer 1 is 1 minus A1 times A2 inverse X. Okay, now it turns out that these are isomorphisms from, if I say, okay, if I look at the, I want to take the inverse, I have a unique inverse of gamma 2, that maps me back to some set gamma m. It's the same set that gamma 1 maps back to. That set gamma m is the Morey cell. That's that periodic pattern we kept seeing, right, in the picture. Okay, so that Morey cell has a Morey superlattice, right, given by R sub m. Okay, so I kind of talk my way through this backwards. Okay, so what this is saying is we actually have a continuum model for disregistry, very concrete, and this really tells us what the Morey cell and the Morey superlattice is, because the Morey cell is simply the cell at which gamma 1 and gamma 2 are repeating. I mean, remember, so when gamma 1 and gamma 2 are the same, you're seeing the same picture, okay? Okay, so basically when you go through, when you move through here, from here to here, or here to here, whatever it is, or any period, you go across the unit cell, right? Then that's, let's say, whatever order of magnitude that is, then you're crossing the the gamma 1 and gamma 2, the dysregistry one time. Okay, so one in real space moving through the Moire cell once is moving through the unit cell of the other layer once. Okay, so that's okay. So we have this nice picture. Okay, now so now we want to. Okay, so I said that I could characterize the displacement, right, in terms of the of these dysregistries. Okay, so now I can define a cap U1 and a cap U2, right? Those are the real space dysregistry. So I'm going to solve this problem in real space. Okay, so now we put all this together and we have an elliptic PDE, right? We have an elliptic PDE on the Moire cell gamma M. Okay, and so now notice here we added in the U2 minus U1 here and the U1 minus U2 because when we have the displacement in, then the effective dysregistry is changing, right? Because the atoms are shifting. Okay, so that's just taking care of the shifted configuration. Okay, so this is our. Okay, so if I take two bilayer 2D materials, I put one on another, and I want to know what the displacement is. This is really an excellent model. I don't see how you could do better than that. I mean, the generalized stacking fault energy is so accurate. You just can't do better than that. Okay, so okay, now it gets even easier, of course, if you're dealing with the same material. If you're doing graphene on graphene or molybdenum disulfide on molybdenum disulfide, then the interlayer energies are the same because the interlayer energies are isotropic. And then we also we can exploit some symmetry by uniqueness of the energy minimization. U1 is equal to minus U2, or you can exploit the symmetry. Okay, so then at the end of the day, you just have to solve for U1, and that's just given by this problem here. Now, actually, I don't think I need to even have this term in there. Okay, so it's even simpler. All right, and so now again, let me emphasize that we ended up with a problem on a periodic domain. Okay, but once we solve that problem, then we can go and reconstruct the atomistic positions. Okay, we can reconstruct the atomistic positions from this relationship. So we can map cap U1 back to little u1. Okay, so this is our formula to reconstruct the actual atomistic positions. Now little u1, right, is periodic on gamma 2. Okay, on the other hand, we're going to sample it, but this here is actually aperiodic. So as R1 moves through lattice 1, if I look at it modulo the lattice, I look at it modulo lattice 2, this is essentially, remember, sampling uniformly gamma 2. So in fact, so even though you have a continuum model that is periodic, when we can actually extract a aperiodic atomistic structure from this, okay, and then that's what we then will feed into our density of states or our electronic models, okay. So all right. Okay, now this shows, again, this just shows, we've seen this before. Now it's nice to look at all the information is really sitting here in the displacement as a function of configuration, right? This is we can represent our little U1 function here, and that just shows you, again, in configuration space, the generalized stacking fault energy. So it shows that we kind of minimize most of the region is actually has a very low stacking fault energy, meaning you're at A, B, or BA. Okay. Now this is maybe even more interesting. This was that 180-degree molybdenum disulfide bilayer, and this has, because of the asymmetry of the generalized stacking fault energy, right? we didn't have a symmetric two-well problem. One has lower energy than the other. Then we actually end up with a hexagonal structure, and here's our asymmetric kind of picture in configuration space, and we look at the generalized stacking fault energy. Okay, now you might say, okay, let's go here and look at, this is just, I keep having the angle 2 degree, 1 degree, 0.5 degree, 0.1 degree, 0.05 degree. So I'm looking at the generalized stacking fault energy in configuration space. So what you see is the width of the layer is scaling like the angle, okay? But then if I map it into real space, it says that in fact the width will eventually be constant, okay? So as we go to this very small angle, the Moire cells get huge, but the width of the interface is constant. Okay, and we have similar things for the 0 degree molybdenum disulfide and 180 degree molybdenum disulfide. Okay, now another interesting thing. Okay, so we have two ways of looking at our problem: real space, configuration space, and so here's the mapping. Now, if you just do your calculation, take the gradient of the configuration space, okay, with respect to x, this mapping, and then what you'll see is that in fact the curl, right, of the real space displacement is equal to the theta times the divergence of the configuration space displacement. Okay, so the curl, right, of a displacement is telling you about the twist. Okay, and that says that in fact that we get the same result looking at the divergence in configuration space. So this is just a picture here, right? This is our generalized stacking fault energy in configuration space, right? With no relaxation, right? We see the high energy of AA, and then the low energies of BA, AB, right? This is what happens after relaxation. And now what we see here is we see the level lines of U1. So we see at the AA points, right, we see a positive divergence. We see a very dense number of lines coming out of there. That means that we have high twist at the AA nodes, and then we have a large regions of slow untwisting in the AB and the BA regions. Okay, so now let's go to P layers. Okay, so now P layers, you might just say, let's try to play the same game. Let's have P displacement functions. Well, first, P displacement functions. Okay, so now we just say, okay, we have to, again, let's go look at a large body limit here, right? We have the intralayer energies of each individual layer, and let's just assume that the interlayer interactions are essentially like J is really affected most strongly by J plus 1 and J minus 1. Makes sense. So here's our model, and we could to know the energy per. So essentially we're interested in the kind of large body energy density of this structure. Okay, and now there's this kind of a collaborator of mine at Minnesota, Kawang, who's just starting out in the physics department. So he's working along with us and has already grown tri-layer graphene. So we're on the way to something interesting. Okay, so now I'm going to start the more formal theory. I may end up going and do the rest of it in the morning because it's going to take this kind of a little bit, take some time to think this through. So so let's start with a little picture, a little 1D picture. So here's 3 layers, no relaxation. Okay, so now let's say I'm just sitting at this point here, right? And now I can describe this configuration, right, by essentially these shift vectors gamma 1, gamma 2, gamma 3. I'm just pointing to the closest node. Okay, I'm pointing to the closest node. Okay, now remember, if I start moving this viewpoint, right, the gamma 1, gamma 2, and gamma 3 are going to be oscillating like crazy, right? on the atomistic scale. But again, we're eventually going to be doing some interpolation, and we'll get a smooth function. But okay, so the gamma j's are the disregistry of the jth layer. And if we just kind of move through this body here, we could view it as some kind of dynamical systems. We can say, okay, we have some translation operator T, and we just add A. We move through the body, and then so gamma is a whole. I'm just using terminology from dynamical systems theory to analyze this. So okay, now we also have a generalization of what incommensurate is for a p-layer system, such as says if you take a sum of p reciprocal lattice vectors, one from each layer, and you sum them to 0, each of them has to be 0. That's the same as that just reduces to the same definition we had when we looked at a bilayer system. And we also have an ergodic theorem, right, for the p-layer system. Okay, we can just describe it this way. We just start with some configuration, and then we just look at all possible viewpoints as we move around in a ball of radius r. It's the same as just sampling f over the whole. Okay, so there's an ergodicity here as well. Okay, so now let's kind of, okay, so what is, okay, so let's say, so I want to develop a continuum model. Okay, so what information, okay, so what information do I really have? What I really have, right, or what I really want to compute is the displacements, right, at the displacements, of the layer, of the atoms, okay? So that means we only want to look at elements of the whole, right, which represent kind of atomistic viewpoints. So let's go back here. That means I don't want to look at this kind of this is saying what's the viewpoint of some guy here, but that guy here doesn't represent any atom at all, okay? I want to say let my viewpoint be this position or that position or that position. So if my viewpoint is an actual atom, then one of the gamma 1s or gamma 2s is going to be 0. Okay, so those okay, so we collect all those viewpoints into something called the transversal of the whole. Okay, we call that X. Okay, so the atomistic deformations are given by mappings U from X to R2. Okay, and then we can describe the displacement of the jth layer Uj, right, in terms of okay, and since now we want to look at the displacement of the atoms in layer J, that means the gamma J is 0, right, for those atoms. Okay, and then we can then map onto displacements and deformations. Okay, so okay, so as I mentioned, what we want to do is we want to describe a site energy, right? Remember, the actual energy of the system is going to be a sum of the site energies of each atom in the system. So the site energy is going to say the site energy of an atom in layer J, right, with configuration omega. So that tells me what that tells me is, okay, so let's pretend that that in fact we're looking at layer 2. That means I want this to be the viewpoint, so kind of move this line over here. So gamma 2 is 0. Then the energy of that atom is going to correspond to the disregistry of all the other. It's going to depend on its environment, and its environment is described by these disregistries with respect to the other layers. Okay, so that's so that's all this says, and so we can describe that environment in terms of the some function v sub j, and that's going to be a function of the differences, right, of it's going to be of the intralayer. It's going to be dependent on where the intralayer atoms are with respect to right? It's going to depend on the intralayer displacements and the it's going to depend on the intralayer displacements. This is going to be the intralayer displacements and the intralayer displacements. So basically, this here just captures the displacement of all the other atoms around that one atom in layer J. Okay, and it says that's going to be that's our site energy. Okay, and then now we end up going again. This packs it in kind of dense, like I said. So now what I'm interested in is an atomistic potential energy per unit area, and what that's given by is, again, I'm going to take this large body limit, but at any fixed radius r, I just sum over. What am I summing over? I'm summing over the number of I'm going to sum over the energy of each layer. J goes from 1 to p. Then I normalize by the number of unit cells, right, in layer J. Okay, the number of unit cells in BR, so so I have to divide the area of BR by the unit cell BJ. That's the number of unit cells. This is going to be just 1 over the number of unit cells in BR. That's all that is. And then this is just taking me to the site energy of each atom, right, in the ball of radius r on layer J. Okay, so this really is, I mean, it's very dense notation. I will confess to that. But what it is, it's saying, it's saying, let me go back here again. It's saying, okay, let these, okay, this is the unrelaxed case, right? Let everybody relax. Now I'm going to sum each atom here has a site energy that's depending on the positions of all the atoms around it. I mean, that's the same thing with like any potential, right? Any two-body potential is the same thing, right? Leonard-Jones potential, gravitational, electrostatic potential. It's all can be written in the same way. It's just a sum of site energies. Okay, the energy of every point depends on where the other points are in the neighborhood. Okay, so this is just the kind of atomistic potential energy per unit area, and that required me to go all over the universe calculating the energy of each atom. Okay, that's what that required. And then now this is where the ergodicity theorem comes from. It lets us pass from this to an integral, right, over, and this again, very dense notation. This just says, I'm just going to go to each, I'm going to sum over each layer, and over each layer, I'm going to integrate over all I'll do a normalized integral over all possible configurations with respect to the jth layer of an atom in the jth layer just sitting there at the origin. Okay, and now I let the atom sit there at the origin, and I consider all the possible shiftings around there and everybody in their displacements. And so this is just some function. And remember, and these integrals, what are these integrals? An atom in x sub j, right, it depends on the configuration of the other p minus 1 layers. Okay, and each layer itself, and the configuration of each of those configurations, this registries, is given by some point in the unit cell. Okay, so this is a This is a 2p minus 1 dimensional torus. That's what that is. So these integrals are over 2p minus 1 dimensional tori. Okay. Now when we did the bilayer, p was 2, and then we went back to our 2-dimensional integral. So what this is telling me is, in fact, we're going to end up with a more sophisticated model. We have a more sophisticated model here required to actually compute multi-layer relaxation. Okay, so I think it's probably a good place to stop here. So so what I'll do is next time I'll kind of review the whole kind of formal theory of this, and then we'll work that out. I'm guessing that'll take a half hour of that. Then the last half hour of the lecture, I prepared a whole lecture on conductivity. I can't get through that. Maybe do something else. But anyway, so feel free to kind of find me and ask questions. I'll see you at 9 a.m. tomorrow morning. Thank you.
We have time for questions? Yes?
You know, the two system that you show first, the layers. So you wrote an energy which is really very similar to the energy of a hexagonal chromatic liquid crystal. Although, of course, the system is quite different because in the plane of the layers it's say solid, whereas in the perpendicular direction is soft. But the kind of mechanics and the symmetries are very similar to what we have.
Well, I'd like to learn more about this. Okay.
Any other questions? Yes?
Yeah, so could you go back to the first slide?
The very first slide? Okay. I'll tell you when to stop. Okay. This?
No, sorry. So next slide. And the next slide. Okay. So here you have two layers, right?
Yeah.
So and why wouldn't, when it relaxes, why wouldn't it form an HCP, hexagonal closed packing? When you're allowing it to relax, why wouldn't it form a hexagonal closed packing? Because I'd assume that would be the minimum energy.
Exactly. Well, are you saying the layers will actually merge into one layer?
No,
No, he's saying they'll be periodic with
Yeah, then-
hexagonal-
Oh, because there's a twist to it. There's a twist. There's an imposed twist on this. It's not. You don't. You know. So this is part of a large material that is kind of it can't untwist. Okay, to get to what you're saying, which would be the energy minimizing state, you'd have to untwist globally. Okay.
And I think you're saying that even with the twist, that you expect it to have
That's what I would
hexagonal
expect.
symmetry. Is that what
Yeah.
you're saying?
Well, you might say, okay, then have some gigantic boundary layer on the edges.
It's large enough.
Well, that's not what people see in experiments. Okay.
Yeah. And it's not what the theory predicts.
No.
Yeah. Questions? Yes.
Is it possible to extend these ideas to calculate the vibration properties and phonon modes and stuff like that?
Well, I think once you have a relaxed structure, you should be able to compute phonon modes. I think, right? I mean,
Yeah.
that sounds a good thing to do. Yeah.
Any more questions? Okay, let's thank Mitch again.